The next presentation is then Tanguy from CEIA from France, and to talk about parallelization with SystemC with a scale concept. So please, Tanguy, see if you can share your screen. Yes, you can. Please. Yeah, welcome, and please start.
This is a joint work that was conducted by Mathieu, Gabriel, Nicolas, and I. And I'll be only the presenter today, but it's really a joint work. So what we're going to be talking here today is how, using the SCale SystemC kernel, we are able to reproduce parallel LTTLM model simulation, so ensure replayability of the simulation. So this is the copyright, just keep it fast. So just to summarize what SCale is, so it's basically a standard SystemC kernel that's been extended to support parallel simulation, and it's been targeting TLM models mainly with temporal decoupling. So the basic idea is to allocate SE threads, several host CPUs that we call workers, and that are able to execute in parallel the SE threads. And in addition to that, we add a specific API that helps ensure atomic evaluation between wait statements. So to comply with the expected behavior that a user that is akin to the SystemC standard would expect. And we also ensure that we have a reproducible execution through what we call repray. So it's not really determinism, we'll be discussing that, but it's, I believe, provides what's necessary for debugging, which is being able to have second execution that is consistent with the first one. So what we just want to do here is, if we take a sequential execution of a SystemC processes with the evaluation of 3 processes and then the kernel phase, we just want to be able to parallelize the evaluation phase. So we're not talking at all about accelerating the kernel phase, though things could be done in this way, but this is not the topic of the work here. So if we consider a simple use case with 2 CPUs that are modeled with process 0 and process 1 that access a memory, we can have actually very different behavior depending on the order that the kernel would schedule the processes. So if we take in the first case, process 0 executes first and process 1 executes afterwards, then process 1 would read an X value updated by process 0.
Short comment, Tanguy. Your sound is good, but it goes a little bit up and down in volume. So sometimes it's a bit weak.
Is it better now? Is it?
Yeah.
It works fine. Feel free to interrupt again if it drops, because usually the sound is good with this headset. So so I was saying in the first case, process 1 would output X equals 2, and in the second case, process 1 would output X equals 0. However, both schedules are perfectly fine with respect to the SystemC standard, which states that the kernel can choose any order it wishes for the execution within the same evaluation phase. However, if we start considering the execution of the 2 processes in parallel without further protection, then we could find a case in which process 1 would actually read a value in the middle of the updates performed by process 0. So this yields to a result that is actually dependent on the execution speed of the host, and which is likely to be non-reproducible due to the lack of atomicity of the process evaluation, and actually not reproducible with the standard SystemC kernel. So how can we prevent that from occurring? So first of all, let us take a look at what we call conflicts and how, before looking at how we're going to manage to handle them. So what we call conflicts is the actual violation of the atomic evaluation of a process. So it occurs when we cannot find an equivalent sequential schedule that would have yielded the same result. So if we look at a sequential schedule, it always exhibits a total order between the processes. So read, write, write to read, and write to write access patterns. Which means that finding conflicts is actually equivalent to finding process access dependency loop. So if we look into these, give an example here, we've got P0 that writes to X, and then P3 that writes to X. So it actually turned out that the value of x at the end of the evaluation should be the one written by P3. So P3 should, if a sequential evaluation would exist that would be performed sequentially, then P3 would have need to run after P0. Same applies to P1 and P2 that needs to evaluate after the updated value by P3. And we also have an additional dependency between P1 towards P2 because P2 is going to write to a value already read by P1. So this is fine. I mean, everything run in parallel and nothing wrong happened. We can still be executing the exact same thing sequentially. However, if we just had, for instance, read to the Y from P0, that means that we add another dependency between P2 to P0. And this triggers actually a loop in the evaluations, which means that there is no equivalent sequential scale. So now that we've stated this issue, how can we really prevent this? So the first idea is that to really identify whether atomicity is violated or not, we need to gain knowledge on the accesses. So we need to perform an access monitoring that would be thorough on the access to shared resources. And we not only need to know what has happened, but when, because it changes the order of dependency between the processes. And performing that requires to have costly barriers to ensure that the accesses are stored into a given order. One also important thing is that not all accesses are problematic. We've seen in the previous example that some accesses do not trigger any issue. So we cannot stop the parallel execution on every access performance. So we need to filter out which accesses are problematic and which are not. And basically, we need to identify which resources are likely shared and prone to errors. And sadly, in the general case, there is no mean to know if a shared resource is going to be actually shared before the evaluation. So if we take the example of CPU models, we can't really know for sure the memory access patterns that we're going to be finding. So we need a dynamic analysis to perform the work. And sadly, we need also rollback because it can happen that we cannot identify shared resources early enough, and we need to be able to roll back. And well, this is something that we don't like to use generally in simulation, but we'll see how it works. So now that we've had stated all the ingredients in the scale recipe, let's move to the actual cooking. So if we take the functioning of scale, so first we're going to be executing several threads in parallel. So P0, P1, and P3 set on worker 0, worker 1, and worker 2. We're going to be monitoring their accesses. So first, let's say that P0 is trying to access X. Well, this is fine, it's the first one to access it. Then P1 also tries to access the same variable. So we're going to deny access to it because we know it's going to likely trigger a dependency. And the same applies to P2. And finally, we're going to resume the execution of the remainder of P1 and the remainder of P2 in a second part of the evaluation phase that we call the sequential evaluation phase. So we're going to go through all the steps here. So here we need to find a way to classify the addresses and decide whether or not we need to yield the execution for the sequential phase. And we'll do that through an FSM-based heuristic that I'll be detailing right after. And in the end, once we perform the whole execution, we want to be able to check that we find an equivalence kernel. And this is going to be performed through an asynchronous conflict check. And we'll need to roll back in case an issue arises. So this is just a quick example of how instrumentation is done. So we just use a MEM instrumentation function that usually, if we look at this example, we've got a CPU process that on every instruction, when it's starting to perform memory accesses which have impact on its neighbors, we just perform the instrumentation. So we gain the access type, read write, and the physical addresses that is concerned, and the side of the access. And based on this instrumentation, it will actually suspend the worker executing the process, and it will also build the worker dependency graph to execution. And the actual access is performed afterwards. So how do we know which address we must, which resource we must stop? So I'm going to be mixing a bit of address and resources because in the case we're usually looking at, considering CPUs accessing a memory through TLM accesses, so the shared resource is usually the memory. So excuse the confusion. So to begin with, all addresses will be considered as no access, so no one has ever accessed them. And so the first actual process that would access this address in read mode, for instance, would change the state of this address to a read exclusive state, and in which state no one else can actually write to this variable since it's been read. We want to prevent any future write access that would cause a dependency between the current owner X and the writer not X. So this is what is depicted with this kind of arrows. Sorry. And so based on these states, we can also move to a read shared state in which several processes accesses only in read mode to the same variable. And this is fine. I mean, several processes can share data and without stepping over each other's foot. So this is something that we can accept. And it's only if someone tries to write to the same data that we're going to unschedule and yield this process. And the same applies for a variable that is owned, in which sense only one process is allowed to read and write to it during the simulation. So one very important property to notice when you look at this FSM is that there is no dependency of type read to write, write to read, or write to write that can occur between two processes during the parallel evaluation, which on each memory access always triggers the evolution of the FSM. So we call this property a zero dependency. And this has very strong benefits. The first of one is that we can perform the instrumentation and the memory access without putting barriers around them. So this really reduces the cost of instrumentation. And the other good property is that all the memory accesses that are performed during the parallel phase, we can record them independently per worker. We don't need to actually determine a total order of their execution. It is what's going to be happening afterwards in the sequential evaluation that's going to make a difference in the event of actual dependencies. So this really improved the parallelism, the performance of the parallelism in the execution. And finally, another property is that in the case where there is no process that is yielded for a sequential phase, then there's no conflict at all, and we can just move on to the next evaluation phase. So I said it before that the FSM starts in a reset state. One needs to notice that sometimes, and very often actually, addresses change owner during the execution of application. So we need to be able to actually forget the previous state of the execution of the variable to use a new one for the remainder of the simulation. So for instance, if you take the Derish application, it can execute process in two passes, one in the x-axis and then in the y-axis. So this means that the data in red here is going to change owner throughout the execution. So what we have settled for is that we can reset the FSM when an unscheduling occurred during the previous evaluation. And this turns out to provide good results, and we've implemented a fast reset strategy. So in terms of conflict and rollback, just one important thing I wanted to state is that we are able to perform the conflict checking in an asynchronous manner. So looking for loops into the dependency stemming from the accesses can be done, which can be costly and sometimes can be done asynchronously. And we can resume the execution without waiting for the results. and we'd only collect the result afterwards. And whenever we collect valid results, we can store process order, the equivalent sequential process order that has been performed, and this can be reused for replay. And once upon a time, regularly, I mean, we are able to checkpoint the simulation state. So if we're in a valid state, that means that we've detected no conflicts so far. We're able to checkpoint the simulation and save the whole process state. And afterwards, when a conflict is found, then we're able to roll back to this state, use the replay order that we've saved to move forward to the problematic evaluation phase, and then execute sequentially the evaluation phase, which ensures that the simulation actually do progress. So I'm saying I'm running a bit out of time. So one important thing that Mathieu stated is that we need to be able to have good parallel workload to really gain in simulation speed. So we need to have processes starting at the same cycles. And usually when you use temporal decoupling, what you find is that two processes commit their wait time, but they're not aligned with the quantum. So you turn out with one process starting at one step and the other one at another step. So you've got no parallelism at all. And so in the models we've been using, we've set up some additional features so that the wait time that is actually committed to the global SystemC time is always that of the quantum, and that the offset is kept in some sort of quantum keeper for the rest of the simulation. The quantum keeper offset just accumulates, but we are sure we execute processes in parallel, which brings more significant parallel workload to be exploited. So in terms of performance, of course, the monitoring is costly. And we compare here with the use case where processes, CPUs are modeled with QEMU as an instruction set simulator, which means that it's running extremely fast. So the memory accesses is what makes for most of the simulation time, and adding some instrumentation to it has an impact. So the cost of monitoring here for some use cases like up to 40%, or the cost of the rollback, the checkpoint rollback and resimulation accounts for an additional 10%. So for half the simulation speed that you would get while leaving the simulation undeterministic and unreplayable, you are able to have still a simulation that executes with a good level of parallelism while ensuring debugging capabilities. And so if we just take a quick look at results we obtain on Linux benchmark, on application running on top of a Linux software stack, we've been able to have gains up to times 13 for 32 workers and 32 simulated cores with respect to the reference implementation. And we've got even more significant gains when looking at the replay run, because in those cases, you don't pay the cost of checkpoint rollback. You just execute the simulation using parallel processes that you know are parallel, and then sequential processes that in the order that you know will not yield any error. So this can bring a higher performance. And all in all, one important thing to understand is that the performance really depends on the application patterns. And for instance, considering Linux software stacks, we had to add a feature to actually monitor the privilege level in the model CPU to make sure that Linux itself is always evaluated sequentially, because we've exhibited that some memory access patterns of the Linux kernel itself were problematic and induced too many rollbacks. So this is something we really want to dig into more. So in conclusion, so Scale really provides practical means to ensure atomic process evaluation and provide replay in simulation. Still, it halves the performance with respect to the indeterministic execution speed, and it requires rollback support, which comes with constraints on the model. I mean, for instance, you can't write to output files, and there's some limits that comes with the checkpoint mechanism that we've used. And but it's successfully provide acceleration as long as the shared resources, the actually sharing of resources is limited. So one drawback is that you need to monitor shared resources, and this usually requires designer knowledge and times for the annotation. So as a future work, I mean, we would like to be able to provide more help to the designer to analyze where their models need to be annotated. And we would also very much like to study the impact in performance of more complex memory hierarchy with several levels of sharing, so that you would have a monitoring that would be finally, we would like also to dig better into what triggered loss of performances when looking into the kernel phases of the Linux application. And this could very well trigger to new tricks to accelerate simulation. Okay, I think I'm a bit slow, so I think maybe I need to hand over, and we'll take questions afterwards.
Yeah, thanks a lot. Thanks a lot, Tanguy. We are almost perfectly on time, a little bit sleeping. Also to you, if you can provide your slides, either your pointer to them, that would be helpful, I think, for everyone.
Yes,